Let's talk about logarithmic functions and how to turn them into exponential form. This is a logarithmic function. Logarithmic functions look like this. Log base b of y equals x. When you have something written in that form, you can rewrite it as an exponential by keeping the base as b, your exponent is now x, and setting it equal to y. So when we look at this guy right here, we would say that the base is 6, that the y is 36, and that the x is 2. So log base 6 of 36 equals 2 can be written as 6 to the second power equals 36, which is true, but it's also how you do it. Write in exponential form. If you are given a logarithmic function, okay, and you're being asked to turn it into exponential form, logarithmic functions are usually given to you as log base b of y equals x. Now you can turn a logarithmic function into an exponential form by doing b to the x equals y. So my b is 14, my y is this huge fraction, and my x is negative 2. So I would rewrite log base b, where b is 14, as 14, because b is 14, to the negative second power is equal to 1 over 196. Which is true because negative exponents move things to the other sides of fraction bars, and then 14 squared is 196. So this is a true statement. Well, that's how you do it. Rewrite in exponential form. This is a logarithmic function. And so when I see logarithmic function and I want to turn it into exponential form, I make it look like this. Log base b of y equals x. Because turning that into an exponential function is going to be me calling this b to the x equals y. So that would make our b 2, that would make our y v, and that would make our x u. So this can be rewritten as 2 to the x, which is u power, equals y, which is v. And that's how you do it. Rewrite in logarithmic form. This is exponential form. I like to call exponential form as b for base to the x power equals y. Once you have that in exponential form, once you letter things up, I can change that into logarithmic form by doing log base b of y equals x. So b would be my 64, x would be my 1/2, and y would be my 6. So this can be rewritten as b log base b, which is log base 64, of y, which is 8, equals x, which is 1/2. And that's how you do it. Rewrite in logarithmic form. This guy is exponential form. Exponential form I like to write out as b to the x equals y. In order to turn that into logarithmic form, we write out log base b of y equals x. So if I were to look at this, my b is going to be 1/5. This is nice. My x is x and my y is y. So rewriting this as a log isn't so bad. Log base b is log base 1/5 of y is still going to be y equals x, which is still going to be x. Sometimes the letters switch around a little bit, which complicate things, but in this case it was pretty straightforward and lots of fun. Rewrite in logarithmic form. This is an exponential function. I like to label my exponential functions as b to the x equals y. Then to turn that into logarithmic form, we write out log base b of y equals x. So that would make my b u, my x is negative 14, and my y is v. So writing that out as a logarithmic function, I have log base u of v equals negative 14, which right now means absolutely nothing, but the whole purpose of this was to rewrite it in logarithmic form so we could do future problems. Evaluate log base 5 of 125. Whenever I'm given an evaluate problem, I like to set it equal to x. Because what I like to do is I like to compare this to log base b of y equals x. So then I can rewrite that as an exponential function, b to the x equals y. So doing that, I can rewrite this as b, which is 5, because my b is 5, okay, to the x, which is still going to be x, equals y, which is 125. And you might be looking at that and saying, oh, that doesn't help me very much. It does if you use the same base formula. 125 happens to be 5 times 5 times 5, which is 5 to the third. And if you have 5 to the x equals 5 to the third, the same base formula says that x equals 3, which makes sense. 5 to the x equals 5 to the third means x equals 3, and that's going to be your answer. So what is log base 5 of 125? It's just 3. So maybe I should have just circled 3 and not x equals 3 because x wasn't part of the original problem, but you get the idea. The answer is going to be 3. Evaluate log base 3 of 1 over 243. All right, whenever I'm being asked to evaluate and it's not an equation, I'm making an equation by setting it equal to x. Why do I do this? So I can compare it to the original log definition, where log base b of y equals x can be turned into b to the x equals y. Now that I have this information, I could say, all right, well, b is 3 and y is that fraction, x is still x. And so I can write out 3 to the x power equals 1 over 243. Now, right now, you're like, what do I do? Well, first things first, if you have 3 to the x power and this is just the beginning of logs and stuff like that, chances are that number right there can be written as 3 to the something power. And it can. This happens to be 3 times 3 times 3 times 3 times 3, 5 times. So that's 1 over 3 to the 5th. Now, we're not quite done yet. What I want to do is I want to make this look like 3 to the x equals 3 to the something. That's not what we have. This is 3 to the x equals 1 over 3 to the something. So I'm going to turn this into 3 to the x equals, why don't I move that up and make the exponent negative, 3 to the negative 5th. Now the same base rule says that if 3 to the x equals 3 to the negative 5th, then x just equals negative 5. So x equals negative 5. Now I'm not going to circle x equals negative 5 because technically x wasn't in the original problem, so I'll just say negative 5 is going to be my answer. So after doing all of that, log base 3 of 1 over 243 is negative 5, baby. Simplify 12 to the log base 12 of 144. There's a log rule that says that if you have a base and its exponent is log with the same base, essentially the base to the log same base cancels each other out and you just drop down the m. Okay, so what happens here is since this is 12 to the log base 12, these guys cancel each other out, and this simplifies to just 144 regular. Nothing crazy, nothing fancy, it's just a rule. Simplify 9 to the log base 3 of 20th power. There is a rule that says if you have b to the log base b of m, the b log base b cancels each other out, and you're left with just m. Now you're looking at this and saying, buddy, that's not at all what you have. Oh no, you're right. You're absolutely right. That is not what I have. What I have is I have 9 to the log base 3 of 20th power. I can turn 9 into 3 squared. So now this is 3 to the second power, and this is log base 3 of 20. Okay, so what I can do is 2 to the log base 3 of 20 has me multiplying exponents. We're going to multiply exponents here. So this becomes 3 to the 2 log base 3 of 20. Now this guy right here, okay, this guy right here, this log has me with a 2 in front of it. Whenever you have a 2 in front of a log, make it the exponent of the stuff inside the log. So now this becomes 3 to the log base 3 of 20 squared, which is 400. Now the 3 and the log base 3 cancel each other out, and we are left with just 400. Tricky. Simplify into one logarithm. When subtracting logs of the same base, for example, log base b of m minus log base b of n, what you do is you simplify them into one logarithm but divide the inside. So this becomes log base b of m over n. These guys have the same invisible 10 as a base, so this follows those rules. So log base 10 of 3 minus log base 10 of 8 is log base invisible 10 of 3 over 8. And that's it. That's all you have to do. Simplify into one logarithm. There's 2 log rules that we're going to follow here. One log rule says that if you have a number in front of a log, so log base b of m, and there's a number there, you take that a and you make it an exponent, so this becomes log base b of m to the a power. So that's the first thing that we're going to do. I have a 6 in front of here that I'm going to move to the u, and I'm going to have a 6 in front of here that I'm going to move to the v. So this becomes log base 3 of u to the 6th power plus log base 3 of v to the 6th power. Now, the second rule that we're going to take a look at is whenever you add logs of the same base, so for example, log base b of m plus log base b of n, you combine them into one logarithm by multiplying the insides and making it log base b of m times n. So my m in this case would be u to the 6th. My n in this case would be v to the 6th. And since they both have the same base, this simplifies to log base 3 of u to the 6th, v to the 6th. And that's our guy. Simplify into one logarithm. Now, if you watch all of my videos in order, you've seen me do this step by step, so I'm not going to write out all the steps as much, but this is what I notice. I have a 6 living in front of this log right here, so you can turn that into an exponent by moving it to v. So this becomes minus log base 4 of v to the 6th power. Nothing happens here, but what I have is I'm subtracting 2 logs of the same base. When subtracting 2 logs of the same base, you divide the insides left to right. So this becomes log base 4 of u over v to the 6th power. And that's how you do it. Expand log of 6 times 11. If you're multiplying 2 things inside of a log, it must mean you must have added to get to that point. So if I want to expand this, I would turn this into log base invisible 10 of 6 plus log base invisible 10 of 11. Okay, because when you add logs of the same base, you multiply the insides. So if you're multiplying the insides, that must have meant that you added logs of the same base. So that's how we expand that little problem right there. Expand log base invisible 10 of u to the fourth over v. Whenever you're being asked to expand a log, you're asking yourself what must have been done for us to get into this situation in the first place. I see two things, an exponent and then I see division. Always start with the multiply, divide stuff first when expanding before you deal with the exponent. Now when you divide two fractions, it must be because you subtracted logs. So the rule is log base m, or log base b of m, minus log base b of n equals log of m over n. And of course I'm using the invisible base 10 for this guy because I have the invisible base 10. So in order for me to get here, I must have done this. So I must have originally had log base invisible 10 of u to the fourth minus log base invisible 10 of v. Now the other thing that I have is I have an exponent living with u. Just bring it out. So now it's 4 log base invisible 10 of u minus log base invisible 10 of v. And that's how you expand. Expand log of the cubed root of x, y, z. All right, there's two ways that I can approach this, but the way I'm going to approach this is this way. I notice that cube root is attached to everything. So I have log of x, y, z to the 1/3 power. So what I like to do is I could do this one of two ways. And I think maybe the easiest way is bring that 1/3 out. So I have 1/3 and I am going to put this in brackets on purpose to make a point of log base invisible 10 x, y, z. Now all these guys inside the log are being multiplied to each other, which means you must have added them to get them in that position in the first place. So I'm going to keep 1/3 out here in brackets. U are the same as log of x plus log of y plus log of z. Now that 1/3 is still lingering out there. So I'm going to distribute that 1/3 to make this 1/3 log of x plus 1/3 log of y plus 1/3 log of z. And that's going to be our answer. Now, another way of approaching this is maybe once I got this point, I distribute the 1/3 to everything, and then you do this part, and then you do the 1/3 part. But this all worked out in the end anyway, baby. Use the change of base formula to simplify log base 4 of 5. Now, the change of base formula is used when you have a calculator of basic log functions. I can't throw that into most calculators. Yes, there are some scientific, maybe an internet calculator or an app. Some of the TIs work for this, but I really need to do the change of base formula. The change of base formula says this. If I give you log base b of m, I could turn it to log any base of m over log any base of b. Now that could be base 5, that could be base 12, that could be ln. But I like to view this as log base 10 because now I can do this in my calculator. So u would be my m, u would be my b, so this is the same as me calculating log base invisible 10 of 5 over log base invisible 10 of 4. And when I throw that into a calculator, I get 1.1609, so I'll do 1.161. Change of base formula. Use a change of base formula to simplify log base 9 of 71. The change of base formula says that if you have log base b of m, you can write that as log base, any base really, but I'm going to do invisible 10 of m over log base invisible 10 of b. Now again, you could use any base. You could use e, so you could do ln's if you want, but this is the most common way of doing this. So you would be like my b, and you would be like my m. So I could go to a calculator and type out log of 71 over log of 9. Remember, most calculators don't have this. They have base 10. The invisible log is the base 10, so now I can throw this into my calculator. And when I do, I get 1.9400, so I'll do 1.94. And that's how you do it. Solve log of 5x equals log of 2x plus 9. The nice thing about a problem like this is you have a log base invisible 10 of blah 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 equals log base invisible 10 of blah blah blah. And in order to get rid of log base invisible 10, I pretend that you guys are exponents and make 10 my base. What this allows me to do is this allows me to use the rule that if I have 10 to the log base 10 of stuff, these guys cancel out and I can just drop down the stuff. So 10 to the log cancels out and whatever's inside drops down. 10 to the log cancels out and whatever's on the inside just drops down. Now it's a regular old Algebra 2 problem. So you would subtract 2x. Actually, it's an Algebra 1 problem, but who's counting? 3x equals 9. Divide by 3, cross u out. X equals 3, x equals 3, x equals 3. And I look at this and make sure that if I were to plug 3 in, I don't get any negatives, and I don't, so this is good, baby. Solve negative 10 plus log base 3 of n plus 3 equals negative 10. Well, let's get log all by itself. So let's add 10 to both sides and magic happens, because if we cross u out and cross u out, that's nice. So I'm left with log base 3 of n plus 3 equals nothing. Now, this n is trapped inside of a log. How do I get it out? Well, I pretend that both sides are exponents and I take whatever base this is and make it the base. Okay, now what this does is allows me to manipulate the rule that if I have b to the log base b of stuff, those guys cancel each other out and the stuff drops down. So n plus 3 drops down. That's going to equal 3 to the 0th power, which is 1. Subtract 3 from both sides, cross u out, n equals negative 2. And if I go up here, I'm allowed to plug in negative 2 because I'm going to get a positive log. You're not allowed to have log of a negative number, but plugging in negative 2 gives me log base 3 of 1. And so this is going to be my answer. Isn't that neat? Solve ln of 2 minus ln of 3x plus 2 equals 1. All right, so first things first, let's combine these ln's. Ln's follow the same rules as log. So if I'm dividing, or subtracting rather, ln's, I'm going to divide the insides. So this guy becomes ln of 2 over 3x plus 2. And that's going to equal 1. Now, in order to get ln gone, I need to get rid of ln. I'm going to pretend that ln and 1 are both exponents and make e the base. E to the ln of stuff crosses the e and the ln, and you just drop the stuff down like so. That's going to equal e to the first power, which is just e. Okay, now in order to solve for x, what I'm going to do is multiply both sides by 3x plus 2. This is not going to be the most pleasant guy on the planet. Multiply both sides by 3x plus 2, but that cancels out. 2 is going to equal e times 3x, so this is going to be 3ex, and e times 2, so plus 2e. If my job is to solve for x, I'm going to subtract 2e from both sides minus 2e. So on the left, I now have 2 minus 2e equals 3ex. Divide everything by 3e. And to write it out nicely, I'll get x equals 2 minus 2e over 3e. And we'll leave it like that. Okay? Not the easiest problem, but also not the worst. Solve log base 6 of x plus 1 minus log base 6 of x equals log base 6 of 29. The first thing we want to do is we want to combine these logs. Whenever you subtract logs of the same base, you multiply the insides. So this becomes, divide the insides. So this becomes log base 6 of x plus 1 over x equals log base 6 of 29. Now that we have a log equaling a log, what we can do is we can make believe that these two guys are exponents and make 6 a base. That'll allow us to cross 6 to the log base 6 out on both sides, leaving us with x plus 1 over x equals 29. Now we multiply both sides by x. That crosses out. X plus 1 equals 29x. In order to get x all by itself, why don't we subtract x from both sides? Okay, so 1 is going to equal 28x. Divide both sides by 28, and you get x equals 1 over 28. Tricky, but fun. Find the inverse of y equals log base 3 of 4 to the x minus 4. Whenever finding the inverse, the first step that you're going to want to do is swap the x and the y. So we'll do x equals log base 3 of 4 to the y minus 4. Now we have to find a way to get that y out of the log. So the first thing that we're going to do is get rid of the log by pretending both sides are exponents and making 3 the base. That allows us to cross u out. So 3 to the x is now on the left, and that's going to equal, drop down the 4 to the y minus 4. I'm going to add 4 to both sides. Okay, so this becomes 3 to the x plus 4 equals 4 to the y. Now this is where it gets a little iffy. That y is still trapped, right? So what I need to do is bring that y down. So let me rewrite what I have here. 3 to the x plus 4 equals 4 to the y. In order to get rid of a base of 4, what we're going to do is log base 4 both sides. Okay? And what that allows us to do is cross that out and bring down the y. So now I have log base 4 of 3 to the x plus 4 equals y. Let's flip-flop that, call this y inverse. Y inverse equals log base 4 of 3 to the x plus 4 is going to be my guy. Tricky, tricky, tricky. Find the inverse of y equals parentheses 4 to the x minus 1 to the 1/5. The first step of finding an inverse is swapping the x and the y. So x is going to equal 4 to the y minus 1 to the 1/5. Now, what I probably want to do is get rid of that 1/5. So let's take the 5th power of both sides, right? Let's 5th power both sides. That gets me x to the 5th equals, these guys cancel out, so 4 to the y minus 1. Let's add 1 to both sides. So that gets me x to the 5th plus 1 equals 4 to the y. Now, I left this space on purpose because in order to get rid of that 4 base, I need to log base 4 both sides because that'll allow that guy to cancel out. So log base 4 both sides. So you become log base 4 of x to the 5th plus 1 equals y. Switch, flip-flop, y inverse is now equal to log base 4 of x to the 5th plus 1. That's going to be our guy. Strange problem, but we did it. Solve 4 to the 2x plus 3 equals 1. It's possible that we're going to need a calculator for this, but we'll see what happens when we get there. We'll see. First things first, that 4 is ruining everything. Let me rewrite this out. Okay, 4 to the 2x plus 3 equals 1. Now, why did I leave all that space? Well, when I have stuff in an exponent, I need to make it no longer in an exponent, okay, especially my variable. So the way you do that is you log base b both sides. So if I log base 4 both sides, that crosses out. So you drop down the 2x plus 3. Now, here's a fun little fact. Log base anything of 1 is 0. So I don't need a calculator for this. All I have to do is subtract 3 from both sides. That gives me 2x equals negative 3. Divide everything by 2. And x equals negative 3 over 2. And that's our guy. Solve 4 to the negative 2x times 4 to the x equals 64. I'm going to solve this without the use of logarithms, and this is how I'm going to start this problem out. Okay, if I'm multiplying terms of the same base, what you're going to do is add the exponents. So 4 to the stuff times 4 to the stuff is going to be 4 to the stuff plus stuff. So negative 2x plus x. Now that I have that on the left, I notice that 64 is a really convenient number given the fact that I have 4s of bases here, because 4 to the third power, 4 times 4 times 4, happens to be 64. So this left side, negative 2x plus x is negative x. 4 to the negative x equals 4 to the third. If you have an equation where the same base equals each other, that means the exponents equal each other. So that's me circling. Negative x is going to equal positive 3, which means positive x is going to equal negative 3. So that's how you would solve an equation just like that. No calculator needed. Solve 6 to the negative 2x times 6 to the negative x equals 1 over 216. All right, first things first, no calculator needed. If I multiply terms of the same base, add the exponents. So the left side becomes 6 to the negative 2x plus a negative x. And we'll clean that up when we have to. I also noticed 216 is an awfully convenient number because 216 happens to be 6 times 6 times 6, or 6 to the third power. So now that I have 6 to the stuff equals blah, 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 6 to the stuff, I'm on the right track. On the left side, I notice negative 2x plus negative x. I can simplify that to negative 3x. And on the right side, I notice, well, wait a minute. 1 over 6 to the third, I can just bring that up here and make that 6 to the negative 1, or negative third. Now that I have 6 to the blah equals 6 to the blee, I can set blah equal to blee, like that. So I can write out negative 3x equals negative 3. Divide both sides by negative 3, divide both sides by negative 3, x equals positive 1. All right, time to solve some exponential equations that require log, which will also require a calculator. So, first things first. If I give something to you in the form b to the x equals y, I can rewrite that as log base b of y equals x. So you would be like my b, even though that's a b, don't get freaked out. You would be my b, you would be my x, you would be my y. So I can turn this into log base 3 of 17 equals b. Now, right now, many people might have a calculator that can pull this off, but I'm going to pretend that we don't. So I'm going to use the change of base formula that turns this into log base 10 or ln. Either way, it's fine. The change of base formula says that if I give you log base b of m, you can make that log base invisible 10 of m over log base invisible 10 of b. Now I can throw something like this in my calculator, because I could just do log invisible 10 of 17 over log invisible 10 of 3. Throw that in my calculator, so let me go off to the side and do that quick. And I got 2.5789, so we'll go with 2.579 equals b, or b is roughly equal to 2.579. So yeah, now we're kind of getting into the, we're going to need a calculator territory to do some of these problems. Not too much fun. Solve 5 times 18 to the 6x equals 26. Well, I got to get x all by itself, so the first thing I'm going to do is divide both sides by 5, which is not going to be awesome at all. 18 to the 6x is going to equal, what is that, 5.2? Great. Now, here's the thing. This is in exponential form. I need to get rid of that exponent. So here's an option. What if I log base 18 both sides? Log base 18 both sides, like that. Squeeze u in there. Okay. What that does is that crosses out and leaves me with 6x equals log base 18 of 5.2. Now, some nicer calculators, graphing calculators, would be able to pull this off, but I'm going to pretend that we don't have one of them fancy calculators, and maybe we just have our own cell phone calculator that does regular logs. Okay? Remember, log base b of m can be changed into log invisible 10 of m over log invisible 10 of b. Okay, so what I can do to put this into my calculator is I can turn this right side into log of 5.2 over log of 18. And of course, these are the invisible tens that are seen in most calculators. So let me go off to the side and find out what that guy is. All right, so not pleasant at all. Let's write it up here. 6x is going to equal roughly, we'll do 3 decimal places, 0.57039, so we'll do 0.570. Now, I still have to get x all by itself, and I'm going to divide both sides by 6 to do that. So let's run back to our calculator and do that quick. Just a quick typey-type. And x is going to equal roughly 0.0950, so we'll do 0.095. Okay? So, yeah, that's how you would do that terrible problem. Solve negative 6 times e to the 8n plus 8 minus 3 equals negative 23. All right, this is going to be rough. Let's start out by adding 3 to both sides. All right, so that gives us negative 6 e to the 8n plus 8 equals negative 20. So far, not so bad. This is where it gets bad. I want to get rid of that negative 6, so we're going to divide negative 6 from both sides. So that gets me e to the 8n plus 8 equals negative 20 over negative 6 is just going to be 20 over 6. Now, you might be thinking, what's all that space for? Well, I have to get rid of this e and drop that down. So why don't I ln both sides? Ln of e to the stuff allows the ln and the e to cancel out. And I could just drop down 8n plus 8. Now what I have to do is go off to the side here and find out what ln of 20 divided by 6 is. So I'm typing that into a calculator right now. And yeah, you're going to need a calculator for that. That's not mental math, boys and girls. I ended up getting 1.2039. So we'll do 1.204. Okay. So what we do now is we continue the problem as normal. Subtract 8 from both sides. When I do that, I get negative 6. So hold on, 8n equals negative 6.796. Then we'll divide 8 from both sides, like that. And when we divide 8 from both sides, we get n equals negative 8495. So we'll do negative 0.850. Yeah, pretty gross stuff. You're definitely going to need a calculator with this. So, all right, we are being asked to graph this logarithmic function. Now, logarithmic functions, generally speaking, with no attachments, are going to look a little something like this. You have your coordinate plane, everything lines up against the y-axis, and it kind of curls up like that. Okay. Now, when I graph logarithmic functions, and I know I do it differently, so this is kind of special, I look for three things knowing the behavior. Okay. I want to find when I have log base b of when this guy is equal to 0. When it's equal to 0, what that gives me is that vertical asymptote that allows me to line this guy up. So this gives me like the wall, the vertical asymptote. So I want my parentheses to be 0, and that's going to guide my one x value. My other x value is going to be found when I figure out what x value gives me 1 inside the parentheses. What that does is that allows me to say, well, log base b of 1 is 0. Isn't that nice? So I want that. And the last thing that I'm going to look for is when I can get my parentheses to be the same number as the base. Okay, log base b of b is 1. Now what this should do is this should give me a place to line things up, a point here and a point here, and enough information for me to have like a nice little curve going on. So I'm going to look for these three x values. Once I get these three x values, it gives me those y values. So x value number 1, okay, x value number 1 that I care about is the number that allows my parentheses to be equal to 0. Now we can do this mentally. X minus 1 equals 0 means that x value is going to be 1 because we would add 1 to both sides. That's going to be point number 1. Point number 2 is the number that allows this parentheses to be 1. So if I have x minus 1 equals 1, add 1 to both sides, that gets me an x value of 2. The third x value is going to be the x value that makes my parentheses b, which is 5 in this case. So x minus 1 equals 5, add 1 to both sides, you get 6. Okay, now that I know that, I can do some simplifying. Okay, so if I have x equals 1, I have my vertical asymptote. Don't need to do any math, that's just my vertical asymptote. Don't do any math at all. When I plug in 2, I get log base 5 of 2 minus 1, which is 1, which I know becomes 0, plus 3. So 0 plus 3 is going to give me 3, so that's a point that I can use, 2, 3. When I plug in 6, that gets me log base 5 of 5 plus 3. Log base 5 of 5 is 1. 1 plus 3 is 4. So that gets me another point. So now I have a couple things that I can do. I have my vertical asymptote that I can draw out, and that's going to happen when x equals 1. So let's do that. Vertical asymptote. This is where my log is going to line up and kind of hug against that line. Then I have 2 points, 2, 3, so 2, 3, and 6, 4. So attempting to draw this out is going to be fun, but my line is going to kind of hug up against this red line for now, and then at some point it's going to start going towards that blue line and start curling over. Now, best line ever? Absolutely not. Not even close. Accurate enough for me to get a couple views on YouTube? 1,000%. But, you know, other teachers would be like, well, sir, dummy, couldn't you just say translate to the right one and then up 3? Yes, but with the base being 5, that changes the game slightly. So I want to make sure that I'm using that part of the game appropriately. But, you know, this is how you would do the problem, and I did it. So leave me alone. Graph y equals 4 times 2 to the x. Now, looking at this, we know that this is exponential growth, which is going to look like this. So probably the easiest thing to do is pick a couple values, right? Pick a couple x values, plug it in, see what happens. Okay, so why don't I pick x values of -1, 0, 1, 2, 3, and we'll go from there. Okay? Nothing crazy about exponential functions and graphing them. For the most part, it's a matter of understanding the behavior and just graphing it. So if I were to plug in -1, that would get me, and let me show myself some more space, 4 times 2 to the -1 power, which is going to be 4 times, let's drop that down to the bottom, 4 times a half is 2. Okay, so plugging in -1 gets me 2, -1 gets me 2. Now we're going to see patterns emerge pretty quickly, which is going to make our life easier, and maybe we could stop using this table over here. 4 times 2 to the 0 is going to be 4 times 1, which is going to be 4. So I get the point 0, 4. 4 times 2 to the first is going to equal 4 times 2, which is 8. So the pattern that you might start seeing is, oh, wait a minute. This is exponential. That's my multiplier. These guys are just doubling every time. So without having to do anything, I know that you're going to be 16. So if I plug in 2, I get 16, so that guy right there. If I plug in 3, that's going to be 32, way too much space. Now, going backwards then, if moving to the right 1 unit doubles my number, then moving to the left 1 unit halves my number. So 2 becomes 1, moving to the left 1 space. 1 becomes a half, half becomes a quarter, and now we start seeing my line hover the x-axis. So you look like you. Here's the part where I'm going to ruin everything and try to draw this out. Okay, so we hover nicely, hover nicely, hover nicely, start to increase, start to increase, start to increase, and everything is gone. And that's the best I can do. Oh, that was so good. I started out so strong, and then this happened. That happened. But you get the idea. You get the idea. It's supposed to look smooth. It clearly does not, but you get the idea. You draw your points, you draw your curve. In a perfect world, I know how to use this pen thing that's currently in my hand, but you know what? Hey, you get what you pay for. And you pay nothing unless you have YouTube Premium. In which case you pay like $9.99 a month? I don't know. Thanks for watching. Love you. Like and subscribe. Graph this exponential function 2 times a half to the x. Now the base here is 1/2. 1/2 is in between 0 and 1, which tells you that this guy is going to be exponential decay. It's going to look like that. Now the best way to handle an exponential decay problem is you're going to focus on negatives, right? Negative x values, and then eventually we're going to hit a pattern. And once we hit that pattern, we can be like, you know what, this is just ridiculous. And you start putting some numbers in. So let's pick -3, -2, -1, 0, 1, 2, and then see what happens after that. Okay, now negative exponents are never fun, but that's all right. We're going to do y equals 2 times 1/2 to the -3rd. Whenever you take a fraction to the negative exponent, you flip it and make it positive. So this is actually 2 to the, what's 1/2 flipped? Oh, 2 to the regular third. 2 to the third is 8. 2 times 8 is 16. You become 16. So I have a point, -3, +16. Let's put a dot right there. Next guy, 2 times 1/2 to the -2nd power. 2 times, let's do that flippy again, and make it squared. So that becomes 4. 2 times 4 is 8. So the next point we get is -2, +8. 2 times 1/2 to the -1st is the same as 2 times 2 to the +1st, which is 4. Wait a minute. Wait a minute. 16, 8, 4. These are just going down by a half every single time, which makes sense because my multiplier here, my base, is a half. So I don't need to do anything more. When I plug in 0, I'm going to get half of 4, which is 2. And when I plug in 1, I'm going to get half of 2, which is 1. And when I plug in 2, I'm going to get half of 1, which is a half. right? And so this just goes down by a half every single time. You're at 2, you're at 1, you're at a half. We'll put you at a quarter. We'll put you close to the x-axis. And you can see how things just kind of level itself out as I showed you there. So now is the part where I ruin everything, and I try to draw this to the best of my ability, which is always very bad. But I'm going to have this curve that's going to level out on the x-axis. I missed them. I'm missing them. That's all right. That's all right. That's all right. I kind of like the picture. I'm very happy with it. Normally I don't draw these well at all, so I'll stick with this. I'm fine with it. But this is exponential decay because you can see my common ratio, my multiplier, is a half. So we're literally taking half every single time. So maybe you start out with a chart and you realize halfway through, I don't need this. And then you just start, using common sense to add a few more points. A savings account balance is compounded annually. If the interest rate is 2% per year and the current balance is that much amount of money, what is the balance, or what will the balance be 8 years from now? All right, so we are going to use a typical percent increase formula over a year. Okay, now what that could look like is that would look like A equals A sub O times 1 plus R to the T. Now, A is the amount that you get when all is said and done. This is going to be the initial amount. Okay, the initial amount. R is going to be your rate as a decimal. Okay, your rate as a decimal. And T is going to be time in years. Okay, so interest rate is 2%. That means nothing. I want 0.02 because you're going to divide that by 100 to get your decimal. Okay, you are my R. My current balance, ooh. Oh, okay, never mind. So that's going to be my initial. I was thinking maybe that would be my new, but no, they still want us to go 8 years from now, which is T. Okay, so I have everything I need to just plug it in and do some math on a calculator. You're definitely going to need a calculator for this one. So my amount is going to be A equals 1,430 times 1 plus 0.02 to the 8th power. Now, again, this is just a calculator problem. If you want to do a little bit more simplifying, you could do 1,430 times 1.02 to the 8th. So let me go off to the side on my calculator and figure that out. Okay, so I ended up with 1675.473, blah, 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 blah. I'm purposely doing that, reminding myself that, ooh, this is money. So my answer is actually going to be $1,675.47. You're not going to round up, you're going to round down. And that's what you do with the regular percentage formula. An architect is designing a tapered office tower where the ground floor, floor 0, is the largest and the floor space is reduced by 5% per floor. That sounds awful. If the ground floor has an area of that much, what is the area of the 9th floor? All right, so we're going to kind of create our own equation based off of like a percentage formula. Now, a typical percentage formula is y equals an initial amount times the quantity 1 plus or minus whatever rate you're talking about to the whatever power over time you're talking about. Okay, things are different here. We're not necessarily talking about a rate. We're not necessarily talking about time. And in this case, we're talking about like a building that I guess is designed like this and each floor goes up. I don't know. It's very bizarre. But as the floors go up, the areas decrease over time. So I guess that's what we're dealing with. So the equation that I'm going to use is the area that I want. So the area that I want is going to be the initial floor. So we'll call A floor 0 times 1. Since the area decreases, that's going to be minus R. So this is R as a decimal, which means 5% is 0.05. okay? To the t power is going to be the floor, so t is going to be the floor that we're dealing with. All right, so the area that I care about is going to be the area of that 0th floor, 1140, times the quantity 1 minus r, which is that 5%, to the t power, which is the 9th floor. Very strange problem. Okay, now if I want to do a little bit more, 5% is 0.05, right? So 0.05, 1 minus 0.05 is going to be 0.95 to the 9. So this is where you're going to run to your calculator and do a little bit of math. So let me do that quick. And I ended up with 718.484 blah, blah, blah. So it looks like they're rounding it to the nearest one decimal, so we'll do 718.5 meters squared. Strange problem, but we were able to use percentages to make it work anyway. A savings account balance is compounded continuously. So this involves the continuously compounded interest formula. That is going to be the total amount equals P times E, that's right, the number E, to the RT. P is your principal, that's your starting amount. Okay, principal, I never remember which principal it is, I think it's U. A is the total amount, E is the number E, rate is your rate as a percent. So rate as a percent, and then T is the time that they give you. All right, so if the interest rate is 3%, that means R is 0.03. And the current balance is that. What will the balance be 5 years from now? So you're my principal and you are my time. So this is a matter of you saying A equals P, which is going to be 1854, times the number E to the RT, which is 0.03 times 5. And now it's a calculator exercise. And I ended up with 2380.583 blah blah blah. Since this is money, $2,380.58. Continuously compounded interest formula. Fun stuff.